today we will continue our topic, that is Riemann integrable functions. Okay. So in last lecture we have seen example, that is some constant function was there, and we have shown that every constant function is Riemann integrable. Okay. Now then we have another example. The example is we have a function here defined as f of x is equal to 1 when x is rational, and when x is irrational the value of function is minus 1. Okay. Now we have to prove that this function is not Riemann integrable over the closed and bounded interval 0 to 1, but mod of this function is Riemann integrable. Okay. So we have to prove that this function is not Riemann integrable over closed and bounded interval 0 to 1. So for that purpose we have to find first the upper sum, lower sum, then upper integral and lower integral. If upper integral and lower integral are not equal, then function is not Riemann integrable. Okay. So we calculate upper and lower integral. So we have already given a function. Now we will take some general partition. Okay. So let partition is, okay, first point our x naught is equal to 0, then some point x1, x2 up to xn, which is nothing but last point 1. So you have taken some partition, any arbitrary partition of the interval 0 to 1. Okay. Now see the function f of x is equal to 1 and minus 1. 1 when x is rational and when minus 1 if x is irrational. Okay. Now if we consider any partition, any subinterval of the this 0 to 1 interval, okay, so this is 0 and this is 1, this is 0. Now there are infinitely many rational numbers and infinitely many irrational numbers in this subinterval. In this interval, similarly, there are infinitely many rational and irrational numbers between any subintervals. Okay. So in this 0 to 1 interval, we take partition. So we get subintervals. Now in each subintervals, there are infinitely many rationals and irrational element numbers. Okay. So at rational, if x value of x is rational, the value of function is 1. If value of x is irrational, then value of function is minus 1. So our function is like either we take value 1 or take value minus 1. 1 minus 1 minus 1. And since number of rationals and irrationals are there, infinite number of irrational and rationals in the interval, the function varies between 1 minus 1, 1 minus 1 and so on. Okay. So in each subinterval there is a value of function take value 1 and function also take value minus 1. Okay. So we can write, now we have minimum value of the function, that is small mk, in the subinterval, case subinterval is nothing but minus 1. Why? Because in each subinterval function take only two values, either 1 or minus 1. So in each subinterval minimum value of the function is minus 1. Now again in each subinterval maximum value of the function is plus 1. Wait, why? In each interval or subinterval function take only two values, 1 or minus 1. So minimum value of the function is in each subinterval is minus 1 and maximum value of the function in each subinterval is plus 1. Okay. So its capital MP is plus 1 and small mk is minus 1. Now we will calculate lower sum and upper sum. So later on lower integral and upper integral. So for lower sum, you know the formula. Lower sum nothing but the summation of mk delta xk, where small mk minimum value. And this is the length of subintervals and summation varies from 1 to n. That is summation over whole partition or whole subintervals. Okay. k is equal to 1 to n. Now m small m k is fixed, it is minus 1. We can take it out later on outside this. So we'll put the value of small m k is minus 1 here into delta x k. So take this minus outside. This becomes summation of delta x k and k varies from 1 to n. Now sum over is subinterval and this is nothing but length of subinterval and summation varies from k is equal to 1 to n. So this is nothing but the length of whole interval 0 to 1 and length of this interval is 1 minus 0 1. So summation of delta x k varies from 1 to n, that is length of whole interval 0 to 1 is 1. So 1 into minus 1 is minus 1. So lower sum it becomes minus 1. Okay. Now we know we have taken P as any arbitrary partition. So take any partition, we are getting lower sum as minus 1. So if we take least upper bound of set of all lower sum for this function, we know the LU will be minus 1. Why? Because the set contains only one value, minus 1. You take any partition, lower sum will be minus 1. So set of all lower sum contains only one value, which is minus 1. So least upper bound of set of minus 1 is this value, minus 1. And LUB of lower sum, that's what the lower integral. So lower integral must be equal to minus 1. See, take any partition, we are getting lower sum as minus 1. So LUB of set of all lower sum must be minus 1. Okay, because the set of all lower sum contain only fixed value, which is minus 1. Now we will calculate upper sum and upper integral. Okay, now we will calculate upper sum and upper integral. Okay, now we know the formula for finding upper sum UPF, which is nothing but summation capital MK into delta xk and summation that is form k is equal to 1 to n. That is summation over whole subintervals. Now again we know maximum value of function is fixed for each subinterval and this is plus 1. So this becomes summation k is equal to 1 to n, one fixed value for each subinterval into delta xk. Now 1 into delta xk is nothing but delta xk. So summation of delta xk is length of kth subinterval, but here summation and it varies over whole subinterval. So sum of length of each subintervals, that is nothing but sum of length of each subinterval is nothing but the length of whole interval, and our whole interval is closer bounded interval 1 to 0. So sum of length of each subinterval is equal to length of the original interval, and length of our interval 0 to 1 is 1. So this becomes 1. It is 1 delta xk, summation delta xk, and summation delta xk is 1. So upper sum becomes 1. Okay. So you take any arbitrary partition P, or upper sum is 1. Okay. So set of all upper sum for this function f with respect to any partition has a fixed value, which is 1. So if we take greatest lower bound of the set UPF such that P is partition of interval 0 to 1, then this will be plus 1. Why? Because you take any partition, upper sum for this function will have fixed value 1. Set of all upper sum, the greatest bound of set containing upper sum for the function will be plus 1. Why? Because this set has only one value, fixed value, which is 1. You take upper sum for the function f, this function f corresponding to any partition, you will get a fixed value 1. So greatest lower bound of the set containing 1 is 1. Okay. So and this greatest lower bound of set of all upper sum, that is what? Upper integral. So upper integral of the function from 0 to 1 is equal to plus 1. So here upper integral is plus 1, lower integral is minus 1. So upper integral and lower integral are not equal. So function is not Riemann integrable. Okay. Here upper integral of the function is not equal to lower integral of the function. So function is not Riemann integrable. Okay. So for this function we have seen the upper integral and lower integral are not equal. So we have concluded that this function is not Riemann integrable. That is here does not belongs to Riemann integrable function on 0 to 1. But if we take mod of this function, okay, now see, function has either value 1 or minus 1. So if we take mod of this function, so mod of 1 is plus 1, mod of minus 1 is plus 1. So we have mod of f of x, constant function 1. See, if we take mod of this function, so mod of 1, 1, mod of minus 1, plus 1. So mod of this function is constant function equal to 1. Okay. So mod of f of x is equal to 1 is equal to constant function. Okay. And now we have already seen that every constant function is always Riemann integrable. So since this function mod of f of x is equal to 1 is constant function, we know that this function must be Riemann integrable. So mod of f of x is Riemann integrable on 0. So this is the example of function which is not Riemann integrable, but its mod is Riemann integrable. Okay, one of the important example of Riemann integrable functions. Okay. So next example is we have defined a function f of x is equal to x on the closure boundary interval 0 to 2, and we have to show that this function is Riemann integrable on 0 to 2 closure boundary interval, and the value of Riemann integration is 2. Okay. Now we know function f of x is equal to x, identity function. The graph of function is like this. Okay, and we have to focus on this interval 0 to 2. Okay, so here 0, suppose here is 2. Okay, so we have to focus only in this subinterval. So in this interval 0 to 2. Okay, now in this interval we see that for x is equal to 0, function value is 0. For x is equal to 1, value of function is 1. This is identity function. Now see, this function is continuous. This function is bounded. Maximum value of the function occurs at point 2, which is also 2. Minimum value of the function occurs at 0, which is 0. Function is bounded. Also, function is monotonically increasing. Okay. So value of function increases whenever we increase the value of x. If value of a function is 2, if value of x is 2, value of function is 2. If value of x is 1, value of function is 1. So if we increase the value of x, the value of function increases. So this function is monotonically increasing. Okay. So we can write f is continuous, bounded, and monotonically increasing function. Okay. Now we will divide this subinterval, this interval 0 to 2 into n subinterval. Okay. So we will take partition P such that these subintervals, this interval 0 to 2 get divided into n subintervals. Okay. So we will take partition P. So first point of the partition is as usual starting point 0. So that x0 is equal to 0. We take x1 is equal to 2 by n. Okay. We are dividing this interval into n subparts. Okay. Then next point will be 4 by n. Okay, up to somewhere 2 into k minus 1 upon n. Next point will be, so here k minus 1, next point will be 2 into k by n. Continuing this way, somewhere we get 2 into n minus 1 by n, and at last 2 into n upon n, that is last point, which is 2. So xn is equal to, okay, so this is our partition. So we have divided this interval into n subparts. Okay, this is the part we have taken partition of this interval. Okay, now see, length of each subinterval is same. Length of first subinterval is contained the starting point 0 and end point 2 by n. So length of the first subinterval, okay, see, 0 to 2. First subinterval is 0 to 2 by n. So here is 2 by n. So length of first subinterval is 2 by n minus 0. 2 by n minus 0. So 2 by n. Length of second subinterval is 4 by n minus 2 by n. Okay, here is 4 by n. So 4 by n minus 2 by n. So 4 minus 2, 2 upon n. So length of second subinterval also 2 by n. So observe that here length of each subinterval is 2 by n. See, length of kth subinterval, that is I k. Okay, so delta x k, that is length of kth subinterval. Okay, now kth subinterval is nothing but starting point is 2 into k minus 1 upon n, and end point is twice k upon n. So length of kth subinterval also 2 by n. See, twice k by n minus twice k minus 1 upon n. So this is equal to twice k by n minus twice k by n. So minus minus plus 2 into 1 by n. So plus 2 by n. This get cancelled. So see, length of any subinterval is 2 by n. Okay, so we have delta xk is equal to 2 by n. Length of each subinterval is 2 by n. Okay, now function is monotonically increasing. So in each subinterval, okay, minimum. So see, first subinterval 0 to 2 by n. Since function increases as we increase value of x, so function has maximum value at the right end point of the interval. See first subinterval 0 to 2 by n. Here 2 by n is right end point of this subinterval, and it is maximum value of this interval. So maximum value of the function in this subinterval occurs at this point 2 by n. Okay, see f of x is equal to x. Put x is equal to 2 by n. Value of function also 2 by n. Put x is equal to 0. Value of function is 0. So in each subinterval, function has maximum value on the right end point of that subinterval. Okay, so in kth subinterval is twice k minus 1 upon n to twice k. This is our kth subinterval. Okay, so that is kth subinterval. So twice k minus 1 upon n and twice k upon n. This is our suppose kth subinterval. See, twice k by n is highest value in this interval, and this is the minimum value in this subinterval. So maximum value of the function in kth subinterval occurs at this point, and minimum value occurs at this point. So capital MK, that is maximum value or supreme value of the function in kth subinterval, it is occur at right end point, that is twice k by n. This is our kth subinterval is equal to twice. So put this value in this function. Put x is equal to twice k by n. So f of x is equal to x. So f of twice k by n is equal to twice k by n. So we get capital M k is equal to twice k by n. And minimum value of the function, that is small m k, is nothing but occurs at left endpoint. So f of x is equal to x. So f of twice k minus 1 upon n is equal to twice k minus 1 upon n. So minimum value occurs at this left endpoint. So mk is equal to f of twice k minus 1 upon n. So f of x is equal to x. So f of twice k minus 1 upon n is equal to twice k minus 1 upon n. So we have calculated maximum and minimum value of the function in kth subinterval. Okay. Now we have to show this function is Riemann integrable. So for that purpose, we have to show that lower integral is equal to upper integral, and their common value is their Riemann integration. So common value we have to show it is 2. Okay. So to calculate lower and upper integral, we will first calculate lower sum and upper sum. So now we will calculate lower sum first. Okay. So lower sum of the function corresponding to partition P is equal to summation k is equal to 1 to n k delta x. Okay, here small n k, that is minimum value of the function in kth subinterval. Okay. So now we have the value of m k small m k and length of kth subinterval. So we take summation k is equal to 1 to n. Put the value of small m k, that is 2 into k minus 1 upon n into delta x k, that is 2 by n. Okay. So 2 into 2 4 and n into n square. We can take 4 by n square outside because summation is over k. This is equal to, so 2 into 2 4 upon n into n square, and summation varies from 1 to n over k minus 1. So we can distribute this summation. So summation over k, it's up from 1 to n, and minus sum of 1 from 1 to n, that is sum k n times, subtraction and take sum of 1 n times. Okay, this becomes 4 by n square summation k is equal to 1 to n of k minus summation of 1 n times 2. Okay. So this becomes 4 by n square. Now we know sum of k varies from 1 to n. It has a formula, sum of first n natural numbers. So it has a formula, that is n into n plus 1 upon 2. Okay. Sum of first n natural number. Okay. Minus, add 1 n times, so minus n. Okay. So this becomes 4 by n square. Now take this subtraction. So n into n plus 1 minus twice n upon 2. So this becomes 4 by n square. N into n square. N into 1 n minus twice n. So n minus twice n, which is minus n upon 2. Okay. So this is equal to, now divide 4 by this 2. So we get 2 into, and take this denominator inside the bracket. So n square upon n square is 1 minus n upon n square. So 1 by n. Okay. So our lower sum is equal to 2 into 1 minus 1 by n. Now if n tends to infinity, then 1 by n tends to 0. So 1 minus 0, 1, and 2 into 1, 2. So as n tends to infinity, our lower sum tends to 2. Okay. So if n is equal to 1, 1 by 1, 1, 1 minus 1, 0, 2 into 0, 0. If n is equal to 1 by 2, Then 1 minus 1 by 2, 1 by 2. 2 into 1 by 2, 1. So value of lower sum is 1. N is equal to, first we have taken 1, the value becomes 0. Now if we take n is equal to, value become 1. So as n tends to infinity, 1 by n tends to 0. This tends to 1 minus 0, 1, 2 into 1. So lower sum is going towards value 2. So we can write 2. So see, lower sum is tending to 2. So supremum for lower sum is either 2 or greater equal to. Okay. Since lower sum is less equal to, so 2 is less equal supremum of lower sum, and supremum of lower sum, that is what? Lower integral. So 0 to, so lower integral 0 to 2 f of x dx. Okay. Since lower sum is tending to 2, either 2 or number greater than 2 must be supremum of lower sum. Okay. See, lower sum tending to, as n tends to infinity, LP of tends to 0. Okay. If take n is equal to 1, it is 0. Take n is equal to 2, it is 1. Tending to 2 from left side. Okay. So lower sum tends to 2. So 2 or number greater than 2 must be supremum for lower sum. So supremum of lower sum must be greater equal to 2. That is, lower integral must be greater equal to 2. Now we will calculate upper integral. We will calculate upper sum and then upper integral. Okay. So we know maximum value of the function is k in kth subinterval is twice k by n, and length of this subinterval, length of kth subinterval is 2 by n. Okay. So upper sum of the function here corresponding to partition P is equal to summation capital MK delta xt, and summation is from 1 to n. K value is from 1 to n. Now we know value of capital MK and delta xt. This is the limit summation k is equal to 1 to n. Put the value of capital MK, which is twice k by n, and length of k subinterval, which is 2 by n. Now again 2 into 2 4, n into n, n square. So we can take 2 by 4 by n square outside because sum is over k. So this becomes 4 by n square outside, and summation k is equal to 1 to n is on this k. Okay. Now again, this is nothing but sum of first n natural number. So our upper sum become, so 4 by n square as it outside. This is nothing but sum of first n natural number. So we know the sum of first n natural number is n into n plus 1 by 2. Okay. Now take this multiplication. So we can divide 4 by 2. So this becomes 2 by n square into n into n square, n into 1, 1. Okay. So we can take this denominator inside the bracket. So this becomes 2 n square upon n square, 1 plus 1 upon n square. Okay. So this is our upper sum. Okay. 2 into 1 upon 1 by n square. Now again see, as n tends to infinity, 1 by n square tends to 0. Okay. Sorry, this is here n into 1 must be n. So n upon n square must be 1 by n. Okay. So again, as n tends to infinity, 1 by n tends to 0. So 1 plus 0, 1, and 2 into 1, 2. Okay. So as n tends to infinity, our upper sum tends to 2. But see, when n is equal to 1, so 1 by 1, 1, 1 plus 1, 2, 2 into 2, 4. So when n is equal to 1, UPF is 4. When n is equal to 2, so this becomes half, plus 1, that is 3 by 2. So 3 by 2 into 2, which is equal to 3. So first when we put n is equal to 1, somewhere 4. When we put n is equal to somewhere 3. So sum is decreasing as we go on increasing the value of n. And as n tends to infinity, sum tends to 2 from right side. Okay. So this means our upper sum goes on decreasing from 4, 3 to 2 from right side. So minimum value of our set of all upper sum must be less equal to 2. Okay. So see, our upper sum is tending to 2 from right side. Okay. So our greatest lower bound or infimum of set of all upper sum. Okay. So our infimum of UPF. Okay, here as n tends to infinity, upper sum tends to 2. So our infimum of this set of all upper sum must be less equal to 2. Okay, either 2 is infimum or there is number which is less than 2 is also infimum, because our upper sum is tending to 2 from right side. This goes on decreasing. Either 2 is the infimum of the set or there is number less than 2 is maybe infimum for the upper sum. Okay. So what is the infimum of set of upper sum? Infimum of upper sum is nothing but the upper integral. That is our upper integral from 0 to 2 of the function is less equal to. Okay. So we have calculated the lower integral, upper integral. We have known, we have calculated previously lower integral is greater equal to. Now we are showing that upper integral is less equal to. Okay. Then what we can do now? What we observe? That lower integral is greater equal to and upper integral is less equal to. So now we know that one inequality. Okay. We have shown lower integral for this function or this interval and for any partition is greater than equal to. Okay. Now we know that lower integral for any function is always less equal upper integral for that function. Okay. So this is less equal upper integral for this function over the same interval. Okay. And we have again shown that this upper integral is less equal to. Okay. Now observe these inequalities. Lower integral is less equal upper integral, which is less equal to, and lower integral is always greater equal to. So from this we see that these two values must be same and must equal to 2, because these are the two values. One is greater equal to and one is less equal to. Okay. What is the conclusion? That these two values must be equal to 2. Okay. There is only one option for this. This must be equal and equal to 2, because they are greater equal to and they are less equal to. So there must be only one conclusion, and that is these two values are equal. That is lower integral from 0 to 2 of this function must be equal to upper integral of this function, and this must be equal to 2. Okay, because there is some value which is greater equal to, which is less equal to. So there is only one option, that it must be equal to 2. So for this function, lower integral and upper integral are equal, and they are equal to 2. So this function f is Riemann integrable over this closure bounded interval, and its integration, it's the common value of lower and upper integral, which is 2. So and its Riemann integration is equal to 2. Okay. So we have shown that this function is Riemann integrable and its Riemann integration is 2. Okay. Thank you.